Question 1. A chemist made a Beer's law plot with standard aqueous cobalt chloride at a particular wavelength, as shown here. If she tests a sample of cobalt chloride and measures an absorbance of that number at the same wavelength, what is the concentration of the sample? They want concentration of that species, which is on the x, and they give us the y-axis. So, and they also give us the equation, so we can just plug it in. So the absorbance they give us is y in this relationship, so just plug it in. Plug it in and then solve for x. 0.81 minus 0.0997 divided by 150.05, which gives me x is equal to 0.0047, which is A. Yeah, 1A. 2. A spinach solution was prepared to determine the concentration of iron in the spinach. A 10 milliliter sample of the original spinach solution was diluted to a 30 milliliter volume with DI water. The absorbance of the diluted spinach solution was 0.285. Use the calibration plot below to determine the concentration. Similar to the last problem, they give us an absorbance, which is the y-axis, and they want the x-axis. I think there's going to be one more step here, but let's first start by doing that. So they give us the absorbance, which is 0.285, and we know the relationship of this line is given by that, and we want the x-axis, so let's just plug this in and solve for x. Okay, if we solve for x, take 0.285 minus 0.0229, divide by 8,868.2. You get that the concentration of the sample is this. Now, this is the concentration of the diluted sample, and they want the one of the original. So the concentration, however many moles of, what is it, iron? Yeah. However many moles, concentration is moles per liter. And however many moles of iron were in the original sample, it's the same as that were in the diluted sample. But the volume, essentially the liters, was times by 1/3. So if we want the concentration of the original sample, I need to take this number and times it by 3. Because the concentration in a sample that's, a volume of 1/3 is going to be 3 times greater. So take your answer from previously, times it by 3, you get 8.86651 times 10 to the negative 5th, which looks like C, 2C. Great. 3. In which pair do both compounds exhibit primarily ionic bonding? Okay. Well, ionic character is essentially, well, I'm not going to write I don't even know the equation off the top of my head. It's related to the difference in electronegativities. I should do this instead. Alpha means proportional to. Okay, let's look at our answer choices. Hydrogen and fluorine are both nonmetals. They have very similar electronegativities. So, definitely not A. B looks like an okay choice because sodium has low electronegativity, and whatever that is has probably somewhat high. Sodium borhydride, those are both non-metals. They both have relatively high electronegativities. That's also probably not very ionic, so probably not B. Yeah, okay. C, I see an elemental atom, so that one has no ionic character because there's no difference in electronegativity. D, yeah, water is also not ionic really at all because, 2 metals. Okay, so let's see, does answer choice E work? We got rubidium, which is right there, and chlorine. That is pretty much the definition of an very ionic bond because they're so far apart. They have such a great gap in electronegativity. How about the other option, calcium and oxygen? Same deal. very ionic. 3E. 4. Arrange the following compounds in order of increasing smallest left to largest right lattice energy. Lattice energy is going to be dictated by Coulomb's law, which is this. Okay, so as you increase the charge between your two species, you will get a greater force and hence a greater, lattice energy. Because, the force acting between your atoms is going to be proportional to the energy between them. So if you increase the charge between them, you will get significantly greater lattice energies. Also, as you move them closer together, you will get greater forces and you will get higher energy. So let's use these trends to figure out. Now, the most important one, between the two ones we just talked about, which is more important, the distance between them or the charge? The charge is more important. So, for example, I know magnesium in ionic bond is 2+, oxygen is 2-, compared to, sodium's 1-, chlorine's 1-. I can tell you right away that magnesium oxide is going to have a much greater lattice energy as opposed to sodium chloride. Okay, and let's see, is calcium sulfur? I'm assuming calcium sulfide is also sulfur is right below oxygen, so I know these are going to have, let me do it in green too. These are going to be 2+ and then 2-. So I know right away magnesium oxide and calcium sulfide, these are my two very high lattice energy ones. So if we go in order of increasing, that leaves, what does that leave? It leaves either E or B. Now we have to look at the size. Now we have to look at the R-squared. So ones that are closer together will have greater forces and therefore greatest lattice energies. So the smaller atoms are going to have greater lattice energies. So we're comparing magnesium. I'm just gonna see the order. Is magnesium oxide greater or is calcium sulfide greater? So when we compare the two, magnesium oxide is there and calcium sulfide would be right below it. So therefore magnesium oxide is smaller, which means that it's a lower R-squared, which means that it's a greater force and greater lattice energy for B. 5. A chemist is studying diatomic halogen molecules. He determines bond lengths for 4 molecules, which is likely to have the longest bond. So we know if you electronegativity good enough is proportional to bond length. The alpha means proportional to, in case you haven't seen that. So, or I should say, So, because if you can imagine, if you have two atoms and say they have a really strong ability, and there's 2 electrons between them, they're in some orbital. If these 2 atoms can pull harder, they will come closer together, and this bond will get smaller. I think it's pretty intuitive. So you just got to know higher electronegativities will make bond lengths smaller. Oh, actually, I guess that's not proportional to, it's inversely proportional. Oops. Okay, anyways. So fluorine has the greatest electronegativity of all these options. And if let's just find these on the periodic table. So essentially, these are options. We have fluorine bind to fluorine to chlorine, fluorine to bromine, or fluorine to iodide. Okay. And of those choices, so we're looking at these. Of those choices, fluorine has the greatest electronegativity. Therefore, if you want to bind fluorine to something and make it the smallest bond possible, bind it to itself, not something lower than it. Because these choices all have lower electronegativities. 5A. Oh, and I read this problem wrong. Oops. I just told you the shortest bond, but they want the longest bond. Okay, make sure you read the question. Don't be me. 5D. Number 6, when 1 mole of each of the following liquids is burned, which one will produce the most heat? Okay, and then they give us some, in black, they give us some hydrocarbons, and then looks like alcohols. Okay, so looks like we got 2 comparisons here to make. When we're talking about hydrocarbons, well, first of all, when we do combustion, let's just say we're doing some random combustion. You're always going to have like your hydrocarbon is reacting with oxygen, which is making carbon dioxide, and then water. These are always the products, and it's always reacting with oxygen. If we have a bigger hydrocarbon, so if I were to balance this, I know I have 2 carbons, which means that's like 2 or something, and like blah, 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 blah. Anyways, if this were instead like C8 and H, you know, what would that be, like times 2 plus 4, so 18. Okay, if I had that and I wanted to balance this, this would then become like, you know, 8CO2 and like something. I don't know. Anyways, you get the point. There's going to be a lot more bonds breaking and bonds forming if my hydrocarbon is bigger. Therefore, the point I'm trying to make is bigger hydrocarbons are going to produce more heat. So A is definitely not true. Okay, anyways, A is gone. So now we're looking at hexane or one of these alcohol molecules. So here the alcohols, they already have an oxygen bonded in them, so they're already partially oxidized. So if we think, so they're going to release less heat, but let me pull this out. If you remember, if we plot like the energy of a reaction and then like time, maybe, we know an exothermic reaction looks something like this, right? And then our delta H of reaction is not that. That's not delta H reaction. This, what am I drawing? This like gap right here, that's our delta H reaction, like products minus reactants. If we start in one of these molecules that already has oxygen, we are starting with lower energy. Therefore, that would be less because it's already partially oxidized. Anyways, this one's kind of just a memorization question. You need to know that 2 trends. Hydrocarbons are going to release more heat and be more combustible than something that has oxygen in it. So it's not one of these ones. And bigger hydrocarbons are going to release more energy. 6C. Compute delta H reaction for the combustion of 1 mole of ethene and oxygen using the average bond energies given below. Hint, first determine the Lewis structure and write a balanced chemical reaction. Okay, I'm going to start with the reaction. So let's see here. We have ethene, which is C2H4. When we do combustion, oxygen is always the reactant. We're always going to have oxygen as a reactant. And when we do combustion of hydrocarbons, we're always going to get carbon dioxide and water. What I just wrote isn't balanced, so let's balance it. I have 2 carbons on the left, so I'm going to put a 2 in front of the CO2. I have 4 hydrogens on the left, so I'm going to put a 2 in front of this. That gives me 4 plus 2 oxygens on the right, so I have 6 oxygens on the right. I'm going to put a 3 to get 6 oxygens on the left. Okay. Okay, so now what we can do to get delta H reaction is we can kind of do something similar to Hess's law, where you can do the bond energy of the reactants minus the products. So kind of similar to how we can combine delta H formations to get delta H reaction, but instead of doing products minus reactants, we're going to do reactants minus products. Okay. So let's do this. Let's first, let me draw the Lewis structure for C2H4 because that will be important. Now, ethene, in case you haven't gone over orgo yet, this little suffix of the ene means it has a double bond. That's just like in the name, it implies that. Also, if you try drawing it without a double bond, it won't work. But anyways, that's a Lewis structure for ethene. So now let's do this equation. So this is going to equal, let's do our reactants first. let's add up all the bond energies in C2H4. So we have one carbon-carbon double bond, which is going to be 614, and then we have 4 carbon-hydrogen single bonds. So let's do 4 times 413. Okay, so there's C2H4. Let's add on 3 of the O2 molecules. Let me do it in green to be consistent. So O2 is just that, right? And we have 3 of them. And within these 3 oxygen molecules, we have one oxygen-oxygen double bond, so 498. Okay, now let's do reactants. So this is my O2. Okay, now let's do reactants. We have 2 carbon dioxides. Oh, okay, I'm doing it in blue, whatever. We have 2 carbon dioxides. Within carbon dioxide, we have 2 of these CO double bonds. So we have 2 of them, so 2 times 799. Okay, and then we have 2 H2O, which this looks something like this. So in H2O, we have 2 OH bonds, which are 467. That's a horrible 7. Okay. So that should be our equation. Let's plug this into the calculator. Okay, reactants. We have 614 plus 4 times 413. Okay. And then we're going to add on 3 times 498. So for my reactants, I have 3,760 for my reactants. Let's do products. 2 times 799 for oxygen. Or wait, no, I didn't label them. This is CO2. This is H2O. 2 times 799. I'm going to add on 2 times 467. Okay, so now for my reactants, I have 3,760. I'm going to subtract off what I got for the products, which is 5,064. I got negative 1,304, which leaves me with A. And all that was in kilojoules per mole. Not that units really matter here. Okay. Also, in case you got the sign wrong, in case you did products minus reactants, you could use the gut check in this problem to know it's exothermic. So, combustions are always exothermic. You can kind of think like a car. Cars use energy to run, and they run off combustion, so they need to be releasing energy from the bonds. So we know that we should always have a delta H reaction that's negative for combustion. So if you got positive, maybe you could use that piece of knowledge as like a fact check. So if you ever have a combustion reaction, delta H should be negative. All right, 7A. 8. Arrange the following bonds in order of increasing bond polarity. Okay, do we have a periodic table? Where is one? There's one kind of. Okay, anyways, they're all bonded with oxygen. Okay, well, they're all bonded with hydrogen, and we have, what do we have with oxygen, boron, nitrogen, and carbon. Okay. On the periodic table, let's see, I actually can just do this. It looks something like this. Boron's on the left, carbon, nitrogen, and then oxygen. And I know the periodic table looks kind of something like this. I don't know. Anyways, electronegativity increases that direction. Also in this direction. Oxygen is the most electronegative, and therefore it will be the most polar. So hydroxide is going to be the most polar. So it's not A and it's not C. And then nitrogen is going to be the second most, because it has the second highest electronegativity of these choices, 8D. 9. Which one of the following compounds contains both ionic and covalent bonds? Okay, let's see. I'm just going to go through choice by choice. Magnesium's a metal, chlorine's not. This only has ionic. Magnesium's a metal, sulfur's a nonmetal, oxygen's a nonmetal. This has both. Let's see, carbon and hydrogen are both nonmetals. This is purely covalent, you know, quote unquote, purely. Let's see, nonmetals, this is covalent. This is also ionic, so 9B. If that doesn't make sense, what I just did, kind of just loosely applying sort of anything in this region is a nonmetal plus hydrogen, and then all of these are metals. Metals and metals form metallic bonds. Nonmetals and metals form ionic bonds. Nonmetals form covalent. So I think there's also a topic video on bonding, but 9B. Yeah. Also, it's the only one that has 3 species, so I don't know how you would get 2 types of bonds from only having 2 species, if that makes sense. Anyways, 9B. 10. The lattice energy of potassium bromide is blank, given the data below. Note that okay, they're just defining it for us. Okay, this is kind of like another do the products minus reactants sort of deal. So we essentially just got to like add up, like make an equivalent reaction of what I just circled or what I just underlined using all of this info. Okay, let's do that. So the first thing looks like we're going to want this equation, and we're going to want to reverse it. So, oh geez, my hand. Okay, hold on. I'm going to make this look better. I'm going to go into black, which is kind of a sin, but just because it's not colorful. But anyways, I'm going to make it look neat. Okay, so I'm reversing this. Anyways, I'm reversing this. And then this is going to become a positive 394 kilojoules per mole. Okay. Goodbye. Okay. All right. So that's my first one. And then if I want to, let's see, what's going to be next? Let's cancel the potassium solid and let's use this one, I'm saying. Anyways, let's put the solid potassium on this side. So it cancels potassium gas, and that is, I'm just going to leave it as 89.24. I'm going to get rid of the units because they're all going to be kilojoules per mole, and it's going to get confusing. Okay, now we have gaseous potassium. Let's add this one now so we get the ion version. Shoot, parentheses are important. Okay, wait, did I do that right? Yeah, I did. Okay. Potassium, positive ion plus an electron, and that's 419. Okay, potassium looks good now. Now let's move on to changing bromine. So I have half a bromine, well, I have half of a diatomic bromine on my right-hand side. So let's do I'm going to do half of this equation. I'm going to do half Br2 gas. Wait a second. I need to make this solid. Wait. Okay, hold on. I was confused because I did not write that this was already a gas. That's why I was confused. Anyways, I'm going to keep going. Okay, half Br2 gas is turning into 1 Br gas. So I just divided that one by half, and this is half of 193, which is 96.5, I think. Okay, and then we're just going to do the last one to make it an anion. Do we need to... Okay, we're just going to leave it as is. Br gas plus electron turning into Br minus. And that's negative 325. All right. Now, if you were to go through and kind of like cancel these, you'd get like this reaction up here. But anyways, I set it up so that already happened. So I'm just going to now sum together all of these numbers. positive 394 plus positive 89.24 plus positive 419 plus 96.5 minus 325. I get 6, my computer's turned off, 673.74. C, let's see, 10C? Yes, 10C. Let's see, if you want to do sig figs, we're adding numbers together, so you go to the least accurate sig fig, which is that position, which would just be 674. Anyways, doesn't matter. 11. For this question, consider lattice energy to be the enthalpy change associated with the following general reaction. Arrange the following compounds in increasing order from of lattice energy. Parentheses are messing me up. Anyways, lattice energy increases most significantly if there's a charge difference. So let's see here. Okay, my example for that one would be like if you had beryllium, which is like a 2+ in its ionic form, and oxygen, which is like a 2-. That lattice energy is going to be way more than whatever lithium, 1+ F1- would be. That's, I think, like this is the main thing that's going to determine lattice energy. The charge, if it is a greater charge between the ions, it'll be much greater. Second thing is atoms with higher electronegativities will have greater lattice energies. So, like, one's generally up in this region. So anyways, those two rules should be enough to solve this. All right, lithium and fluorine. Wow, just talked about that. Let's see, what's the next one? Barium and sulfur. Where's barium? Down here. And sulfur is right there. And then potassium iodide. And then calcium, different color. Calcium and oxygen. Okay. So calcium is 2+, oxygen is 2-, so is barium 2+, and then what is barium with? Sulfur. These ones are the ones with the 2- charge, which is what I was talking about. So these two are already going to be way more than the lithium 1+, and the fluorine 1-, and then the potassium iodide. These two are going to be way more. So if we're arranging them in order of increasing, I know calcium oxide and barium sulfide are going to be on the right side. So no, and no. Okay, so now we just got to decide which one of these two is more so. If the elements have a greater electronegativity, they will have greater lattice energy. I know calcium and oxygen are going to have greater electronegativities because they're higher up, as opposed to barium and sulfur, which are like down. So let's see, what is this? 11, is that B? Also, if you look at these ones, it's going to be consistent because, yeah, lithium and fluorine are higher up than potassium and iodide. Anyways, 11B. 12. Consider the indicated region A of the potential energy diagram for the interaction of two hydrogen atoms. Which one of the following statements is true about region A? Okay, so first, we have internuclear distance. So this is the lowest potential energy. When we have diatomic hydrogen, this is kind of where they're going to exist. And if we push them together farther, the positively charged nucleuses are going to get closer and they're going to start repelling. And the electrons are also going to start repelling each other in a way that would overcome the covalent bonding. So when you push them together, they're actually going to want to repel and go back down to that state. And then when they're far apart, they're going to want to bond and come together. So I think that's just kind of the conceptual understanding of this graph. All right, anyways, they want to know which one's true, so let's read our choices. A, the potential energy decreases with decreasing internuclear distance. So they're talking about decreasing internuclear distance, so it's like going this way along the curve. And that happens in region A because the attractions between electrons and hydrogen atom nuclei increase more rapidly than do nucleus-nucleus and electron-electron repulsions. This is true. So when we're bonding, we are... Let me do this. So we have the positively charged nucleus, and then we have these negative charges flying around. And then there's two of them. And when we form bonds, this nucleus is going to bond to this electron. And this has to overcome the opposing effect of these electrons repulsing these electrons. And this nucleus repulsing this nucleus. And it has to overcome that. And that's essentially exactly what A is saying, is that the attractions between the electrons and the opposite nuclei are increasing more so than the repulsion interactions. So A is true. B, a diatomic hydrogen molecule will spontaneously dissociate into hydrogen atoms in region A. That's not true. We're going to form the diatomic hydrogen. C looks similar to A, but they're saying the opposite, which is that the attraction forces between electrons and hydrogen nuclei decrease more rapidly than do nucleus-nucleus and electron-electron repulsions. And that's not the case. That would be the case if, let me see. That would be the case, I believe, if we were going this way. Anyways, that's not the case. In this direction, we're forming the diatomic hydrogen, which has the sort of positive and negative charges overcoming the opposite charges. So, what is this? 12A. Nice. Okay. 13. Which of the following is the correct order of increasing bond strength based on the periodic table? Okay, they want weakest left, strongest right. All right, so we're looking at silicon, and we have, okay, the halogens are my options. And the halogens are right here. Bond strength is going to be analogous to bond length. It's kind of comparable to that. When you have elements that are more electronegative, they're going to form smaller bonds, shorter, more compact bonds that are going to be stronger. So silicon, when it's bonded with fluorine, is going to be very close. Let's say it's some arbitrary distance that long, as opposed to maybe when it's with iodide, it's that long, because iodide is not as electronegative of an atom, and it's not going to hold on to silicon's electrons as strongly. So that's sort of the trend here we're looking for. I arrange them in order of the periodic table. Fluorine has the most electronegativity, chlorine second, bromine third, iodide last. Right, because as you go this way, you increase electronegativity. So for these atoms, the highest electronegativity is fluorine. So this, anyways, I'm getting confused. I'm doing backwards arrows. This is decreasing electronegativity. Therefore, silicon fluorine is going to be the strongest, so it should be on the right, 13B. Yeah, and then if you look at the rest of these, that follows the trend that we just described. 14, the possible formation in outer space of that molecule from water and oxygen is described by the equation. Use the data provided below to estimate the enthalpy change for the reaction above. Okay, we did a problem similar to this earlier. We can do, let's see, delta H reaction equals reactants minus products. Okay. So let's see, is this balanced? Yeah, it looks like it. All right, we're just going to take all the bonds on the reactants and subtract all the bonds on the products. So let's take water first. Water has two OH bonds, which is 467. So 2 times 467. And then I'll put this parenthesis as my entire reactant. My other reactant is oxygen. And there is one oxygen-oxygen double bond, so just plus 498. There's my reactants. Let's subtract products. Products, looks like I have 2 hydroxide bonds, these two, 2 times 467, and I have 2 oxygen-oxygen single bonds, plus, different color, plus sort of 2 of these oxygen single bonds. All right, throw this in the calculator. 2 times 467 plus 498 minus 2 times 467. Wait, hold on. Okay, so for my reactants, I got 1,432. Let's do products now. 2 times 467 plus 2 times 204. For my products, I got 1342. Reactants minus products. Delta H reaction equals 90. Okay, yeah, they got 90, and then that's in kilojoules per mole. I'm just looking at that decimal place. I don't know if that's intentional or not, if that's a sig fig thing. Anyways, doesn't matter, because none of the other choices are going to be chosen. So I'm not going to worry about it. 14C. Arrange calcium, rubidium, sulfur, and arsenic in order of decreasing electronegativity. And I don't have a periodic table. Let me see. Okay, give me like 3 seconds if I can pull one up real quick. I'm going to steal one from 2 problems ago. Wow, that synced so quickly. Anyways, okay. All right, let's find these all in the periodic table. Sulfur, arsenic. Where the hell is arsenic? I have no idea. Awkward. What are the other ones? Rubidium. I know what rubidium is. Calcium. Easy. Okay. AS. Where is it? Oh, it's right there. Okay. So those are our 4 elements. Say out loud to yourself what the periodic trend for electronegativity is. You've probably heard it a million times. It goes that way. So sulfur is the highest. Sulfur is the highest, so I know it's A or B. Arsenic's second, calcium's third. Therefore it's B. 15B. Nice. 16. In which of the following molecules are the bonds most polar? Pretty much another electronegativity question. I'm just going to use the periodic table above. Looks like we are always bonding with phosphorus, and our options are fluorine, hydrogen, iodide, bromine. Okay, so our options are the halogens plus hydrogen for some reason. Anyways, the most polar bond is going to be the one with the greatest difference in electronegativity. And I can tell you that all of these, other than maybe hydrogen, I'm not sure, are going to have greater electronegativity than phosphorus. So what we're looking for is the element that has the greatest electronegativity. Okay, okay, so let's see. Hydrogen's right there. It's not hydrogen, I can tell you that. And then those are our halogens. Which one of these has the most electronegativity? That will form the most polar bond. Electronegativity trends this way. Therefore, it is going to be fluorine because that's the most electronegative of these options. 16A. Nice. 17. The melting points of metals are only moderately high because metallic bonding is weak. That's not true. Metallic bonds are pretty strong. Metals have fewer bonding electrons than non-metals. So if we think of like the bonding model, metals typically, they form like these ion cores, and then they'll have like some sea of electrons that are kind of free to flow around between the ion cores, as opposed to more the non-metal model where, maybe you have like your inner energy level, and then there's 2 electrons that are sort of being shared in an orbital. But anyways, my point is that there's a lot of bonding electrons here, so it's not B. C, metals also have relatively low boiling points. That's pretty unrelated. D, the melting processes do not break the metallic bonds. So this is true because when we heat it up and we're going to melt these ion cores are just going to be able to flow around, and we don't actually have to change any of the electron configurations. So D is going to be our right answer. E, metals prefer to be bonded to nonmetals. I do not believe that's necessarily true. So 17, C or D it looks like. Problem 18. Complete the best Lewis structure for the molecule whose skeleton structure is shown below. The molecule has blank total lone pairs. Okay, so the first thing is I see on this skeleton structure they're not showing the hydrogens. They're showing so let's draw on those hydrogens. We know we have 3 on this carbon, and then there's 2 coming off this nitrogen. Okay. Also, we know this has to be true because in order to be neutrally charged, the carbon has to have 4 bonds. So if it only has 1 bond they're showing, I know it has 3 implied hydrogens right there. Which brings me to this carbon. So if we know this carbon has to have 4 bonds, but it doesn't have a hydrogen bonded to it, there's going to be a unsaturation right there. There's going to be a double bond to that oxygen. Also, in order for oxygen to be neutrally charged, we also know it has to have 2 bonds. So, oxygen either has to be something like this, maybe if it's carbon, or something like that. Like there's got to be a double bond. If you're going to see oxygen in an organic molecule like this, it's probably going to be one of these 2 situations. It's not really, you can't have a neutrally charged oxygen that only has 1 bond to it. So, anyways, now let's solve the problem. Let's write in the lone pairs. So, for 2 bonds, 2 bonds and a neutrally charged oxygen, it will have 2 lone pairs. For nitrogen, if it has 3 bonds, it will have 1. So that gives me 3 lone pairs. How did I know this? Because oxygen, or these atoms form octets, which is 8 electrons. I know these 2 bonds account for 4, so I know oxygen needs 4 more, which is 2 lone pairs. For nitrogen, 2, 4, 6, so it needs 1 more lone pair to get to 8. That's how I figured that out. If you go through enough orgo problems, you'll kind of just start to memorize these, which is how I came to it. But these atoms like to form octets, where they have 8 electrons. So anyways, 1, 2, 3. 18C. 19. The structure of triiodide ion has all atoms connected linearly. How many lone electron pairs are the central iodine atom? And what is its formal charge? Iodine is a halogen, so I know it contributes 7 valence electrons, something like this, and then it's also 1 minus, so I know there's going to be an extra electron somewhere. And they're connected linearly, so there's probably a covalent bond, something like that, and then something like that. Okay. And then I need to put the extra electron somewhere. I'm going to put it on the central atom. This gives me a -1 in the central atom, and then sort of like a -1 overall. The alternative to this would be, let's see, we could move these lone pairs onto like a different iodine. So let's compare that. Maybe it's something like this. Covalent bond. That's the same. Then you'd have that. Okay. If we switch it into this, this would then become a 2 minus and then a 1 plus, which would still give us the same overall, 1 minus. So on paper, both of these are possible, but when you're trying to find the best sort of structure that's the most stable and that actually exists in real life, you want to minimize the magnitude of charge. So if we can put a 1 minus charge on one atom, that's going to be better than trying to make these bigger charges on more atoms. It's not as likely to exist. So this is our best option. Also, we're violating the octet rule here because this has, how many electrons does it have? 6, like 10. When you get down lower onto the, so generally the octet rule arises from when you have like a S2, and then you have like the oh geez, when you have like your 1s orbital hybridizing with your 3p orbitals, you get like the 3 like sp orbitals that hold 6 electrons. When you start incorporating the d block, like the d orbitals, you no longer get pure sp hybridization, and you can start sort of violating the octet rule. So iodine certainly has that d orbital hybridization going on. That's why we're allowed to violate the octet rule. That's kind of an aside, and I don't know, you may or may not need to know that to solve this problem. But in case you're looking at that and wondering, like, how is that allowed? It's because you're getting d orbital hybridization. So, anyways, what does that leave us with? We got a -1 charge and then 3 lone pairs, it looks like. So, 19B. Nice. 20. In the best Lewis structure of HCNO, what are the formal charges on carbon, nitrogen, and oxygen? Note the molecule has more than one central atom. Okay, so we have hydrogen, which has 1 valence electron, carbon, which has 4, nitrogen, which has 5, and oxygen, which has 6. Okay, so if we want to start bonding these up to find out what's the best Lewis structure, that's probably going to form a bond. And then if we want carbon, okay, carbon has 2 options now. It can form a double bond and take a lone pair, or it can form a triple bond. So, okay, I'm going to make 2 possible combinations now. We're going to do, that's a single bond, and then we're going to have triple bonded to that, or we can have just double bonded, and then carbon would have a electron pair, lone pair. Okay, and then we're left with oxygen, which in this first case, it would just be like a single bond. 2 oxygen. And then this has 3 lone pairs with a -1 charge. Also nitrogen is a +1 charge. And then in the second case, this would be a double bond, in which it's neutral, but carbon is -1. So these are our 2 options. If you rearrange the electrons, these are going to be our only 2 that give us +1 charges. If you started putting lone pairs on nitrogen, I think we would get +2 charges. Let me try that for example too. So if we wanted to put a lone pair on nitrogen, how would that look like? Then I think you'd get something like this. I don't know if that balances out, but listen, the two best are the ones I drew above. Okay, which one of these are more stable? So they both have essentially the same overall charge, which is neutral, and they both have charge magnitudes of only 1. But this option puts the negative charge on oxygen, which is more stable than putting it on carbon, because oxygen's electronegativity is greater than carbon's. Therefore, oxygen would be more stable holding the negative charge. Therefore, this option's the best. Okay, and what do they ask for? They want the formal charges on each of them. Carbon is neutral. Carbon is neutral, so we're already at A. Okay. Yeah, carbon's neutral, nitrogen's +1, oxygen is -1. 20A. 21. What is the molecular shape around each of the 3 carbon atoms in propine? Okay. Computer turned off. Okay. Let's see here. Carbon is sp3 hybridized with 4 bonds. That's tetrahedral. It has no lone pairs, so it's got to be tetrahedral. Also, with these problems, I don't know how much there is for me to explain. If you look up sort of what molecular geometry is. Maybe I'll do a video on it too. This stuff's kind of just memorization and kind of knowing the names. But if you have something with like 4 bonds, well, you guys probably don't know what dashes and wedges are. But anyways, this shape is called tetrahedral. Okay, this structure, it has 2, and there's no lone pairs. I mean, that's essentially what it looks like, and that is, well, let me label these. This is tetrahedral. This is linear. Linear, okay, so we know we're already at B, which is right, but let's keep going. And then, oh yeah, and then same deal for these two. These two are just that connected in a straight line. There's no lone pairs involved, so therefore it's linear. If instead I had like, I don't know, the reason you would might get bent instead of linear, the best example is probably water, because if you get lone pairs, like why would water be considered bent and not tetrahedral? Because technically it has like 4 bonding regions. It's because like we don't consider these in part of like the molecular shape. Anyways, very simple graphs online. If you look up molecular geometry, I think it's pretty intuitive. Anyways, 21B. 22. What is the molecular shape around sulfur in sulfate? Okay, so sulfur is right under oxygen on the periodic table. It has 6 valence electrons, and there are 4 oxygens here that are bonded to it. Oxygen also has, wait, that's 7. Oxygen also has 6 valence electrons. Okay, and let's see, sulfate. Oxygen is a more electronegative atom than sulfur, so we're going to put these -1 charges on these oxygens. And those are only going to form single bonds. Let me do this instead. Yeah, let me do this instead, actually. We're going to put these -1 charges on these atoms, and then I'm going to move, just for simplicity's sake, I'm going to move these up to there. I'm going to draw double bonds here, because these double bonds will make those oxygens neutrally charged. And then we will get single bonds there. Okay, and that's our sulfate atom. 4 bonding regions, 2 atoms give us tetrahedral, because essentially it looks like this. This is the tetrahedral molecular geometry with those 109.5 bond angles. 22C. Problem 23. Which one of the following molecules has a bond angle close to 104 degrees? Okay, so off the top of my head, I know this is nearly, well, let me do a better symbol. I know this is nearly like 109, so they're really looking for a tetrahedral style molecule that's going to have like 4 bonding regions. So I'm just thinking that off the top of my head. Let me go through these structures and let's see if we can figure anything out. Silicon tetrachloride. Okay, that's a great S. Silicon tetrachloride looks something like this, which obviously has the, like if I drew like a more accurate geometry, it would look like that. In case you don't know bond dashes and wedges, that's what these are. In structures, a wedge means it's coming out of the page, and a dash means it's going into the page. It's just kind of like a way of showing it. But anyways, this is like a tetrahedral structure. So this could be our answer choice. These bond angles are at 109 degrees, 109.5 roughly. So that's pretty close. It's not a horrible choice. All right, let's look at aluminum chloride. This looks something like this. It has 3 bonded atoms and no lone pairs. So this is trigonal planar. And trigonal planar, it like exists all on like one plane. So like it looks something like this. Like, I don't know, you can kind of picture it. They're all existing on the same plane. And this is 360 degrees all the way around. So each one of these is about 120 degrees. So 120 degrees is not really close to 104 degrees. So because that's trigonal planar, I'm going to not go with B. How about carbon dioxide? Carbon dioxide is carbon double bonded with 2 oxygens. That's a horrible O. Okay. Same deal. We're on this molecule exists on like one plane. It's 360 degrees all the way around, which means this is like 180 degrees, right? So that bond angle is 180 degrees, which is not even close to 104, so it's not carbon dioxide. Bromine, tetrachloride, or no, trichloride, oops. Same deal as the aluminum chloride. Same deal, so I mean it's trigonal planar. These are all about 120 degrees. Not really close. All right. 23E, let's see what we got here. Okay, we got sulfur. Sulfur is right below oxygen, so it's electrically the same. And we have 2 chlorines. Okay. So this one, like this option, also has 4 bonding or 4 electron regions. So it does have the sort of like tetrahedral shape. I forget exact names, but it's going to look something like this. Let's actually, let me do that. And then it's like I have a lone pair on the dash and then a lone pair up there. Okay, so this one, in theory, this one would be similar to 109 degrees as well. But you need to know here that this electron pair will actually, this electron pair has more, use different color. This electron pair has more electron density than these bonds. And what it's going to do is it's essentially going to push these bonds farther down. It's going to push those bonds farther down and close the bond angle. So these chlorine bonds, this chlorine bond angle, originally you'd expect it to be about 109. It's going to be down to about closer to 105. So yeah, these lone pairs are kind of pushing in the chlorine atoms, if you can think about like the electron density. So this atom, sulfur dichloride, is going to have closer to 104 degrees. Let me also generalize this real quick. So let me do this. Let's say I had silicon. Okay, let's say I had, this is supposed to be, okay, silicon with like 3 chlorides. This one would have about 107 degree bond angle. Silicon with tetrachloride, let's say that's a dash, and then wedge, and then, anyways, so if that's like 4 chlorines, this one will have about the 109.5 that we expect. And then if you have 2 lone pairs, you will get 105-ish. So another chlorine there, and then, so if you have 2 lone pairs, which was the case we had in E, you'll get closer to 105. So as you add lone pairs, it's going to go down, and these are kind of the numbers you can expect. So for like the tetrahedral style atoms, adding in lone pairs will push the bond angles closer. So 23E. let me check that one. 23E. Scroll. There we go. Okay. 23E. 24. In the best Lewis structure for cyanide ion, NCO-, what is the formal charge on the nitrogen atom? Okay. Carbon has 4 valence electrons, nitrogen has 5, oxygen has 6. And we know we are going to have a minus somewhere, so we're going to need to add in 1 electron. Carbon, let's see, if we're going to want the minus charge somewhere, we're going to want it on the oxygen. So let's see if we can make that possible. If we want that, that would be a single bond here, and then we could do 3 bonds with nitrogen. And then that would make the, yeah, okay. So making this molecule is possible. We're essentially, you're just putting the extra electron on oxygen and then doing a triple bond between carbon and nitrogen. So the formal charge on nitrogen and the best Lewis structure is 0. So what I did here, if that didn't make sense, my logic. Oxygen is the most electronegative of these options. If you don't know electronegativity yet, it trends this way. So of our choices here, oxygen is going to have the highest electronegativity. Therefore, I know if there's going to be a negative charge on this molecule, it should be on the oxygen, if possible. So I kind of tried drawing that structure, and it is possible to draw that. So the best structure would have no formal charge on nitrogen. 24C. 26 and 27. Consider the Lewis structure shown below. The hydrogen-carbon-carbon angle described by arrow 1 would be most closest to, so this is, let's draw that central carbon. Let's say the carbon up there is going in that direction. Hydrogen. And then a wedge means coming out of the page, and a dash means going into the page. It looks something like that. Textbook tetrahedral molecular geometry. This has a bond angle of about 109.5 on all sides. 25C. 26. The oxygen-carbon-nitrogen bond described by angle 2 would be closest to, all right, carbon is our central atom here. It has a double bond up to oxygen, and it has carbon going this way, and then a nitrogen going this way. It's trigonal planar. This is trigonal planar. Nothing's coming into or out of the page. It's, around in a circle. We have 360 degrees total. So each one of these is approximately 120 degrees. And looking at our answer choices, it doesn't look like they're looking for anything more specific than 120. Like, it's not off. Like, we only have one answer choice close to that. So 26 is D. For example, what I was just talking about there at the end is, like, they're not concerned with, like, they didn't give us, like, 119 as a choice, because in this answer up here, we were kind of concerned with the fact that lone pairs and electron density can change bond angles, but that's not really the choice in 26, because we only have one answer choice that's close. So, anyways, 26D. 27. What is the electron group arrangement and molecular shape of SOCl2 as predicted by valence shell electron pair repulsion theory? Okay. So, where do we have the periodic table? Sulfur will, it's not in that first row, so it gets, it can accommodate more electrons. Sulfur likes to have 10 valence electrons, so I know the structure of this off the top of my head. I don't know why I drew that one off to the side. Okay. It's going to form a double bond with oxygen, and then single bond into the chlorines. This is how we get our neutral atom, because this has an octet. Sulfur has the 10 electrons that it wants. And then the chlorines have their 3 lone pairs plus 1 bond, which is what they're going to have in a neutral atom. So if this is our structure, let me draw it in more of a, it's not silicon. Let me draw this in more like the molecular geometry shape. It will look something like this. We got our wedge, which is coming out of the page, dash, which is going into the page. That's a tetrahedral structure. Tetrahedral. And since it has a lone pair right here, we're going to kind of more specifically classify this as a what is it? Trigonal pyramidal. Trigonal. Anyways, I'm going to stop trying to spell that because I'm going to get it wrong. Trigonal pyramidal. There we go. Okay. It's an A. It's an A. All right. Oh, yeah. Okay. So here's the names. So the first thing I was talking about, it being tetrahedral, that is the electron group arrangement. I guess I didn't really give it names. So, like, this is the electron group arrangement because it has 4 bonding regions, but only 3 of those 4 are atoms. So therefore the molecular shape is going to be trigonal pyramidal. So 27D. If this is confusing, if you just Google molecular geometry, there's some like tables that'll come up that are usually pretty useful. Because there's a lot of words in this section, but I think if you kind of look at those graphs and try to memorize a little bit of just what the names are, they're pretty intuitive. Because if you think about trigonal pyramidal, it's kind of just like a pyramid. Like if you thought about this structure, like what it actually is, it kind of looks like a pyramid. I don't know. Just think about it for a little bit. Look at those graphs. I think it'll make sense. 27D. Okay. 28. Use valence shell electron pair repulsion theory to predict the HON and ONO bond angles in nitrous acid. The Lewis structure is shown below. Okay. Let's see here. So that is a electron group arrangement of tetrahedral, right? So if I drew this out, it would look something like this. You'd have, well, yeah, this is fine, right? And then we have two lone pairs, and we know, so traditional electron group arrangement of tetrahedral will have a bond angle of 109.5. If you add on, so I'm referring to, say we had like a tetrahedral arrangement with all 4 atoms. So this arrangement would have a bond angle of 109.5. If you add in one lone pair, that lone pair will push down these electrons and make these bond angles smaller, right? Because that lone pair has a very high electron density, and it will push the bonds closer together, and it will reduce that 109.5. So one lone pair will reduce that bond angle of 109.5 into about 107. Okay. Now, let's consider the next case, which is the case we have with 2 lone pairs. So if you add in a second lone pair, if you swap out one more atom with another lone pair, this will get reduced down to about 105 degrees. So adding lone pairs is going to decrease the bond angles. All right. Oh, wait, that's not even what this question is asking. Okay, way to overanalyze it. This bond angle is approximately 185. Oh, well, actually, kind of. It's slightly less than 109.5. So, no. Could be B, not C. Okay, B, D, or E. Anyways, that's how we figure that out. Let's take a look at, let me draw a line. Let's take a look at the next bond. Okay. We have 3 bonding regions. So if I were to draw this out, it's kind of like single bonded to oxygen, and then like that. It's got 3 regions. This is, by definition, trigonal planar. The electron group arrangement is trigonal planar, and then the molecular shape would be bent. I should start using this convention more often. Anyways. So trigonal planar and bent, and let's see, bond angles. It's 360 degrees all the way around, and this exists in one plane, so these are about 120 degrees. And since we have that lone pair again, it's going to push these bonds closer together, meaning this is something slightly less than 120. I'll just make up, maybe it's 118. I don't know. Anyways, it's slightly less than 120. So looks like E. 28E. Nice. 29. Which one of the following molecules is polar? So in this question, let's not confuse molecules with bond polarity. So I think there have been some questions previously as to what can be a polar bond. So for example, carbon and chlorine would form a polar bond because carbon is much less electronegative than chlorine. So chlorine would get a partial negative charge and carbon would get a partial positive. This is a polar bond, but you can have these bonds in a nonpolar molecule if it's symmetric. So when we talk about molecular polarity, we're looking at asymmetries, electron asymmetries in the molecule. So for A, our molecule looks something like this. And this is symmetrical all the way around. We don't have any lone pairs anywhere that can make this polar, so it's not A. Okay. In diatomic hydrogen, once again, there's no symmetries. Also, our bond is not polar because it's the same atom. Hydrogen has the same electronegativity as hydrogen, so it's not B. Carbon dioxide. This has a linear shape, and there's no lone pairs once again, so there's no asymmetries here. Yeah, because essentially the dipole moment on this side is going to be canceled by the dipole moment on that side. Anyways, that might be a little confusing. There's no asymmetries, so not C. Sulfur dichloride. Let's see. Something like that. This, on the other hand, if I do draw the molecular structure, it might look something like this. Now, this, on the other hand, does have this very high electron density up in this region, and it's not symmetrical. So, D's our choice. N2 is similar to H2. There's no asymmetries, so it's not E. 29D.